the Medical AI Podcast.
Hello, I'm Dr. Felix Beacher, and this is the Medical AI Podcast, a 30-minute thrill ride of big ideas. We talk to a range of top guests, from industry innovators to scientists to philosophers. This is brought to you by Omdia and Informatech, where I'm the head of healthcare technology. According to some estimates, an amazing 10% of patient deaths in the US are related to misdiagnosis. Diagnostics is one of the key examples of how machine learning could revolutionize healthcare. And one company at the cutting edge of oncology diagnostics is the San Francisco-based company ThinkCyte. Joining me is Janette Phi, the Chief Business Officer of ThinkCyte. Janette is an expert not only on the business side, however, but also on the research, on the scientific research. Janette, a huge welcome to the podcast.
Thank you for having me.
So, Janette, I'm very curious to get to know you a little bit better. Could you say a few words about why you entered the field of medical AI in the first place?
Well, I've been in the field of drug discovery and medical research for over 30 years now. And when I was first introduced to medical AI just a short few years ago, I was quite excited to realize that this may be the missing piece that I've been looking for. I've been driven over the years finding ways to add value to true personalized medicine. And at the moment, I'd like to share with you the reason why. About 20 years ago, my son, who was 16 years of age, had an accident, and he was sent to the hospital because he was not able to stop bleeding. And for about 3 days, they couldn't stop his bleeding. And it was a very difficult time for us because we could not understand. He was losing blood just continuously. And it was a very, very difficult time for my family and I. And it wasn't until the third day when one individual who understood and what was happening was brought in, and Dr. Michael Zhang from Stanford, he came in and he said, Janette, I believe I understand what is going on with your son, and treatment is already on its way. And he went from a child that was very, very ill in bed to about 2 hours later, he was up playing video games. And that was mind-blowing to me. It was like, what had happened during the 3 days that was different from what Dr. Zhang had provided. And so because of that, I've dedicated my life to being able to focus on personalized medicine. I don't think anyone should ever have to go through the process that my son and I did. But there's always good things that happen, right? I mean, this incident has inspired my son to join the field of medicine and in science. And right now he is working at a genomics company. And it's inspired me to find ways to improve our process. And I believe medical AI is that piece, that I believe the last missing piece to that puzzle. And how do we remove ourselves from the issues of misdiagnosis? How do we better improve precision medicine, getting to that information, precision medicine faster? And this is what I believe medical AI can add.
Right. Okay. So just because it's a great story, tell us a little bit more about what had led up to that point where your son was properly diagnosed and properly treated. What kind of problems did you have with misdiagnosis running up to that?
Well, a lot of it's not the physician that is the issue, not at all. All the physicians that were there were just wonderful and did the best they could. It was information. It was lack of information, lack of knowledge, because they were running many tests, but not really understanding all the results. And how do I integrate all this information? Because it's all that information coming together that was able to get to the right diagnosis. So when you are encased with so much information. How do you process and how do you integrate all of that? And this is where machine learning and AI can be a very powerful approach to this. And this is what excited me. And so for me, if we can provide that information to more physicians, it would help them to diagnose properly and have the right diagnosis. And not only that, but faster. Instead of 3 days, it could have been done in hours, right? And also, not just that, but let's talk about as we monitor this, each of us are very different. If you think about how, personalized medicine, precision medicine is about taking our uniqueness, understanding that, and then identifying the best treatment for me or the best treatment for you or for our family. So I think that goes hand in hand. And that is, if we can get information faster, better information, we can then make better decisions in terms of treatment selection.
Now, how just on the human interest side, how seriously ill was your son? Was he genuinely in danger, or
Yes.
or what?
Yes. Basically, without being able to stop the bleeding, he would have died.
Wow, I can truly understand why that might have changed your perspective in a very profound way. And how is he doing now?
He's doing fantastic. He is a force of nature in that he has so much passion. And I think that incident has really inspired him to make a difference. And this is why he entered the field of medical science. He wants to make the next wave of difference.
That's a wonderful story, Janette. Now, you've mentioned a couple of different ideas there, but that are closely related. One is precision medicine, and the other is diagnostics. Now, how do those two things relate to each other?
Well, if we can get to more information, better diagnosis, we can begin to link the right therapy for each person.
Yeah.
Every disease that we have, there are multiple treatment options. How do we choose the best? Well, we choose the best by understanding that individual, not as a general therapeutic approach. It isn't start with A, then go to B, then go to C. No, each person has a better selection. Will be with the right information. We can decide, well, this John is best with medicine A. Joe is better with medicine B, right? So that's what we want to approach.
Now, one of the things I really enjoy about medical AI is the impressive variety in the ways in which machine learning techniques can be applied to different kinds of medical data. And that brings me on to ThinkCyte. Now, could you just explain a little about how ThinkCyte's technology works?
ThinkCyte, our technology is using what's called ghost cytometry. It's kind of a cute name. I really enjoy saying that. It's our ability to actually look through a cell. And each and every cell has its own signature. So we call it cellular fingerprinting. And with our technology, we look in each and every one of those cells. We can identify a healthy cell from a diseased cell without even touching it. So hence the reason why we call it ghost cytometry. So what that means is that when you have a cell is like a car, right? It comes in different size, it comes in different shapes. And that's the first thing we look at, the size, the shape of each and every cell. But more importantly, we look at the engine inside that cell. We look at inside the cell to see what is happening inside that cell. So it's like an engine where when an engine is running well, it's a healthy cell. When it is not doing well, like for instance, it's running low on gas or low on oil or sputtering because of air issues and all that, we can actually see what's happening inside the cell without touching it. And that's what's unique about our technology. And we use AI, machine learning, to be able to train our system to recognize a healthy cell from a diseased cell, from a cell that is becoming ill.
Now, when people normally talk about engines inside cells, they're generally talking about mitochondria. Is that what you're looking at? Are you looking at the shape of mitochondria or something like that?
That's a great question. That is actually one piece of what we look at. We look at everything inside the cell, from inside the nucleus to the mitochondria, to the lysosomes, to the organelles, to the proteins as they restructure, as they move around. So not only do we identify what's inside the cell as it changes. So let's use the mitochondria as a great example. When we talk about a healthy cell, mitochondria looks like a jelly bean. If you ever look at it, it does look like a jelly bean. It always reminds me of what the jelly bean looks like as a mitochondria. In a disease cell, that jelly bean will start to slice off or pinch off into, instead of a single jelly bean, it'll be 3 or 4 little balls of jelly beans. So it's changing its shape. It's changing its size because something is happening inside that cell that's causing it to become a diseased cell. Okay. And what we do with our technologies, we can see those changes. We can see as that jelly bean, that very microscopic jelly bean shape changes, we can see what's going on. And that's what's allowing us to be able to very, very quickly identify healthy cells from disease cells.
Now, I would imagine that you could, in principle at least, measure an unlimited number of features inside a cell. I mean, I'm not even a cell biologist, but I could probably rattle off just tons of examples. Now, I guess what you could do is just throw everything into a machine learning model and not worry about what it all means, but hopefully something will come out, which will enable you to conduct diagnostics. On the other hand, what you could do is you could just focus your examination of the cell on features that you really properly understand, like, for example, the morphology of mitochondria and some other things. Now, which of those two kind of approaches do you use?
Well, we leave that to the scientist. Our technology can see. So we're going to take, let's put it this way. Let's approach it from both ends, right? Mm-hmm. We provide researchers to the ability to actually start to map out, to understand every feature within the cell. And not just the feature, but the rearrangement or restructuring of the same set of features. And this is where machine learning is going to become very powerful, because what we're going to do is our researchers are going to go through the process of just saying, hey, I don't know what's in there, but I'm going to find out. And I'm going to try to understand what's happening inside that cell when I give that cell a certain, drug therapy A versus drug therapy B. We're going to understand, we're going to come in with an unbiased nature in terms of saying, let's take a look what's happening. Okay, that's one side of it. Now, on the diagnostic side, we do understand there are certain pathways, there are certain mechanisms or patterns of how the car or the engine is run. We use the machine learning part of it, and we teach the machine to understand very specific characteristics. And from a diagnostic perspective, we look for that. Okay, let's go in. We know what this signature is supposed to look like. Mm-hmm. Through machine learning, let's see if we can quickly bring the patient sample and give them a fast diagnosis, because we know what we're looking for, right? Yeah. So there's that's the both end, and we need both. We need the front end research to continue to feed the machine learning, and because machine learning can only be as powerful as the database you give it, right? And so we need to continue to feed that database, and that's one of the challenges that we are facing right now as a young company, is that database has to start. And that starting database is not going to be a huge, massive database yet. But over time, our goal is to build a large database of knowledge.
Got it. Okay. So where is ThinkCyte currently as a business? Are you turning a profit yet? Are you still seeking venture capital? Do you have collaborations going? So tell me about that.
Well, we are not a profitable company at present. We have raised 2 rounds of funding. And that was about $45 million to be able to move our company into exploring the technology, looking to see, because this technology is so new, so novel, it's a question of how far can we push this technology? What are all the things we can do with this technology? And over the past 3 years, that's exactly what we've done. We've kept the technology internal. We've been partnering with big pharmaceutical companies, medical centers, cancer centers, to be able to see what can we do with this technology. And this is how we were able to identify we have some unique capabilities that we'd like to begin to introduce to the world. And so we're actually doing our unveiling of our first product about 1 month from now at the SLAS conference in San Diego.
Yeah.
So we're pretty excited about that. So we are introducing our technology now to the world.
Fantastic. So, okay, well, let's turn to some specific examples about how this might work in practice. Now, first of all, what disease areas are you working in, and why did you choose those?
Well, I always tell people when we approach this area, think about it as the right hand and the left hand. The right hand is understanding the disease, right? The oncological aspect of it. And we've chosen leukemia. Leukemia has a wide variation of different types of leukemia. And this seems to be an ideal area for us to look at because we are looking at that variability. We are looking at each and every single cellular fingerprint from each leukemia type. So we've chosen leukemia as the initial field to enter into. So we've been working with partners around the world to profile chronic myeloid leukemia, multiple myeloid, AML, ALL, all the different leukemia types.
Yeah.
So that's the first area. The left hand is really, or however way you want to approach it, right or left, the other side is the cell therapy side. So we have been working on various cell therapy profiles, looking for high therapeutic value cells, because those cells, like CAR T cells, CAR NK cells, CAR macrophage, or T cell receptor, all these cells have very unique signature. And as I mentioned earlier, we can see healthy cells from exhausted cells, right, where the engine is not running well. And because of that, we can better identify the cells, the high quality cells for therapy. So we approach both because we believe you need the right and the left hand to really come together.
Okay, now let's say that somebody wakes up with symptoms of leukemia. Obviously, they need to be tested. Now, how would that testing process work currently? And I mean, could you explain what the problems of diagnosis are currently with leukemia? And how would that process work if your kind of system were fully implemented?
That's a great example that I can share with you here. When we talk about leukemia, by the time that you as a person start to feel not well, you're most likely in the late stage of leukemia. So your treatment, your outcome potential has decreased significantly. Really a significant reduction in terms of your probability of being able to survive through the leukemia. What the way that works right now, if you're not feeling well, or you go in and the physician takes some blood sample, they take a tube of blood, and they'll start to actually go through and identify the healthy cells. They'll put a bunch of labels on it. And, I need to label your healthy cells. I need to label your potential leukemic cells that are present, and they'll start to screen and pan through and look to see. And it's all based on labels. Each and every cell needs a label for them to see what that cell is. Okay. It's a very routine process, but it does take a fair amount of time. It takes days for them to complete through that process. Okay. So the different in terms of how we approach things is that for our leukemia process, we actually don't require a label. You would go in, and instead of getting your blood, you're giving your blood, and a couple of days later you get the results. We could actually get the results back in a matter of hours, because there's no labels that are required. Remember, I was saying that we can see the cell untouched, and we can actually see inside the engine inside the cell and be able to identify one cell type from the next. So because of that, we would just take the patient sample and run it right on our machine. There's no labels that are required, and there's no extensive experimental planning that's required.
So to some then, the big difference is in the time taken for diagnosis, correct?
Time, and the fact that because we are unbiased in a sense that we don't require labels to it's like trying to find a needle in a haystack.
Yeah.
You have two approaches. You can either light up that needle so brightly that you can see it with lots and lots of label, right? Or you can label every single piece of that haystack and move it out of the way and identify it as that's not what I want, right? We take a different approach. We run everything through. We don't require a label, and we can run everything through, and we scan untouched without having to put light it up in a as a light bulb. We can actually scan through, and based on its cellular fingerprint, we can identify that single needle in that haystack. Okay.
Now, how could you describe the current standard methodology to kind of bring out the differences with what we're doing here with this kind of technique?
Well, let's use CML as a nice example. In order to identify the leukemic cell, we would need to really label it with CD38, CD138, CD34, CD133 to try to find, is that my leukemic cell? Okay. And then you have to really take labels on all of the negative cells, the healthy cells that are the non-leukemic cells. You need to light that up so that you can move that away from your target, right? So that's one. Now, for our system, we actually can identify those cells based on its shape, its intracellular structure. The example that we talked about earlier, the mitochondria, we know that these blast cells undergo what's called mitochondrial fission. And we can see that the signature changes. And because of that, we actually can identify those blast cells. That, to me, allows us to be able to say, let's not wait until the patient is ill, right? Let's do this as part of our routine checkup.
So it's a completely different model of diagnostics then, isn't it? I mean, it's very radical and super interesting.
And that's what I'm hoping to be able to do, is to make this so accessible, because it's faster. And the moment you don't have to do such extensive level of complex processing, it'll be less expensive. So it becomes affordable. So it becomes a routine process instead of, hey, we can only run that test when you're really ill, right?
Now, do you know what it reminds me a little bit of is I'm trying to think of the name of that glamorous blonde lady who recently got put in prison for fraud with the drop of blood in the box thing. Do you know what I'm talking about? What's her name?
Oh, Theranos.
Elizabeth something.
Yes.
Who am I talking about?
Yes, the Theranos. Yeah,
that's exactly right. Theranos. Now, I'm kind of wondering, obviously, I'm guessing you might... I mean, it does, the concept behind Theranos, I think, is kind of fascinating, right? And I kind of wonder what I think one of the things that people found difficult to accept with Theranos is that you could do everything on the basis of one drop. But I don't see why you couldn't do an awful lot on the basis of one tube of blood. And that kind of is kind of where you're going with this, I think. Is that fair?
Yes, and I think the difference is that Theranos was, well, as we always say, please don't bite off more than you can chew, right? You don't have to have a solution for everything. You just have to be really good at the one thing that you choose to focus on. And I think that's the difference. I think Theranos did have capabilities, but they tried to run, I think, 40-something tests that they could do in a drop of blood. That's just overreaching. I like to take one step at a time. And for me, it's about, can we focus on leukemia? Can we focus on this area and show what we can do? And not, the ability to actually have this as a routine assay for us, or a routine test when we go in for our annual physical, that's not going to happen in the next few years. It will be down the road, but it has to start somewhere.
Right.
And this
Elizabeth Holmes, that's her name, by the way.
Exactly. Elizabeth Holmes, exactly.
You knew who I meant, though.
Yes.
Okay, so let's talk about. Now I realize I want to ask you about accuracy, but I realize, of course, that what we're proposing here is a completely different way of doing diagnostics. So in a way, accuracy is somewhat beside the point, but let's talk about it anyway. If you had 100 samples tested by standard method and 100 samples tested by your method, how would the level of accuracy, do you think, compare?
Well, I think without machine learning, I think that accuracy would be very low. With the machine learning and our ability to look at the cellular fingerprint, and keep in mind, we don't have just a single fingerprint, by the way. Every cell that we look at has actually 4 to 5 dimensions of waveform or fingerprints that we look at. So think of it as an object inside a box. And if you look at that object or that object inside that box and you only look at it from one angle, one view, then you really cannot make out the full capability or those features of that object. So you have to really look at a 360-degree view of that object to be able to reconstruct it properly. And that's exactly what we're doing. We are looking at each and every cell in a 360-degree way to better characterize that object.
Right.
And this is the reason why we needed machine learning, because we as humans, we can't recognize that information that quickly, right?
Exactly. Now that leads me on to the often raised, rather knotty problem of the black box. Right now, is this something that has been raised with you as a company? Is it a concern for you? And I guess the first question actually should be, is your system a black box?
No, we don't believe it's a black box. We like to share how we are doing things and what we are doing. And the reason why I'm saying I'm comfortable with it not being a black box is because we have ways of testing it, right? What we do is we basically look at, okay, here is a leukemic cell based on traditional method. And let's see if we can use ghost cytometry to characterize and sort out the healthy from the leukemic. This is the reason why we built into the system a sorting mechanism, so that when we say we believe that's the blast cells, we can sort out that population and then run genomics testing, run proteomics testing and all that to validate that, yep, you're right, that is the disease cell. So it's no longer a black box if you can actually share with people what you are seeing, what you're doing, and validate them, right? So I think we don't believe in the black box theory. We believe in open science, and science comes with lots and lots of validation, right?
Yeah.
You have to be able to have that.
Now, I was chatting with another leading figure in medical AI recently, and he mentioned to me a problem for regulators and for companies who are producing new products, which is that this is such a rapidly developing field. How are regulators and how are companies supposed to keep up with the rapid pace of development? Because obviously you can't submit a new algorithm to the regulator every week, right? How do you deal with that kind of problem?
Well, we deal with it by actually creating what we call ground truth, right? Ground truth labels, standardization in the process. If I say that I can see an object of a certain size or shape, then you have to create the ground truth that proves that, yes, you are seeing that. And then you run that as a standard routine. And so what you had asked me earlier, if I run something 100 times, how accurate will I be able to see it 100 times? Mm-hmm. Well, we wouldn't be able to release anything out there, and we don't want to release anything out there until we can say that, yes, we can see that 100 times accurately. Because it defeats the purpose of what we're trying to do and what I'm trying to do in terms of looking at removing misdiagnosis, right? And so that, to me, if we are able to prove that here is a calibration tool, here is a standard ground truth label, ground truth object, that we say it's supposed to have that signature, and every single time it has that signature, that's confidence, right? That gives you confidence that our technology is seeing that thing correctly.
Sure. Right? Okay, so are these kinds of technology rapidly growing, or have you found a real niche here?
I think it's growing quite fast. It's probably one of the fastest growing fields I've experienced in my lifetime.
Why do you think that is, Janette?
Well, on some of the latest reports, I'm seeing that the compound annual growth is about 45%. In our field, it's like anything that's 10, 15% or so is already amazing. Yeah. But this is growing at 45%. That's just insanely fast.
It is crazy.
I think a lot of it is because there's a lot of retrospective information that we're now able to realize, hey, this gold mine of information is there. Let's use AI, let's use machine learning to see if we can take that information and understand it better. So that's how you feed the initial process of that database.
Yeah.
And then can we start to, and globalization is also a key factor. People are, when you work with people, it's no longer, hey, I'm in the Bay Area, I only work with Bay Area people. No, every day I'm working with people from all around the world, and we're sharing information. That's what's growing it even faster.
Yeah. Now, let's talk about disease monitoring, because disease monitoring, in a way, is kind of just like diagnosis spread over time, right? So it should, I would have thought, in principle, be fairly easy to extend diagnostics to techniques for disease monitoring. Is this something you're working on as well?
Absolutely. Absolutely, because we are already seeing early evidence that when you have a patient, for instance, in the area of leukemia, and we've been looking at this, when that patient, if you look at that patient's cellular signature, we know that patients that have relapsed at the time of diagnosis, you get one signature. And then at the time, like a year, 2 year, or even patients that are in remission, we've been noticing that there is still a cellular fingerprint difference. Okay. Can we begin to do that disease monitoring and begin to predict if the patient has the high potential for relapse? And if so, can we have a preemptive approach to it so that we can provide a therapy in advance of that patient, being diagnosed in relapse, right? We want to prevent that relapse.
Yeah. Mm-hmm.
And so the only way to do that is to monitor that disease over time.
Okay. Now, could you say something about the potential disadvantages with this kind of technology relative to current methods, standard methods?
Well, I think the biggest issue is going to be how much information can we feed our machine learning? That's the limitation we have right now.
Yeah.
Is that because we don't have our platform out there yet. It will be released, but it will take time for that technology to be in the hands of scientists. And we have to teach our scientists to understand this whole different way of doing science, right? We are really doing it in a very different way. So it is going to take time for scientists to adopt this process. So that's one limitation that we see. The second is really how fast can we feed our database and feed it the right information, because our machine learning is only as powerful as the database that we give it. And I think those are the two key things, is really getting adoption from the scientists to really say, this is a really great way of looking at this. We want to be able to look at it this way now instead of our old method. And the second thing is having them share information with us so that we can feed our database and make it more powerful, and then share that with the world in terms of information.
Got it. Okay. So let me ask you one last question. It is the question I always end with. And that is, could you say something about your favorite example of medical AI currently used that's got nothing to do with your own?
I'm going to answer in a slightly different way, because I've been so focused in a certain vision that I'd like to share my thought in terms of what will be used in the near future. And it's not just ThinkCyte. We hope to be a piece of that puzzle, but it's about true personalized medicine, where we will have the ability to integrate through AI the genetic information, the physical uniqueness of each and every person to identify the best and fastest diagnosis and the best treatment plan. And not just that one-time treatment plan, but over time, as you had mentioned earlier, that disease monitoring process as well. Because I really feel that no parent should ever experience the near loss of their child. And with the amazing advancements in AI today, I think that this capability is closer within our grasp than we ever thought.
I see. One of these days, somebody's going to ask me that, and do you know what I'm going to say? I'm going to say it's Theranos. No, but you're quite right. And look, Janette, it's been a huge pleasure talking to you. I'm so glad we had this conversation, and very, very best of luck with ThinkCyte. I'm sure it's going to be a great success.
Thank you very much for having me on the show.
Talk to you again, Janette. Thanks. Bye-bye.
Thank you. Bye.
Thank you for listening. I'm Felix Beacher. Ping me on LinkedIn for more information on Omdia's services in healthcare technology. See you next time.